Hola chicos, bienvenido a mi clase. Hola Courtney. Courtney, ¿sabes tú que yo estoy estudiando español? Pienso que ella salió. No comprendo. ¿Por qué tú no me comprendes? ¿Estudias tu español? La clase pasada nosotros hablamos español juntos y pienso que deberíamos hablar español contigo juntos también. Será, oh, j'ai dit que je suis, ah, j'oublie français, j'oubliais le français. J'ai commencé à étudier espagnol. Okay. Anyways, pienso que deberíamos hablar español juntos en la clase de Zoom. Uh, por lo tanto, tengo esperanza que ustedes están listos porque yo voy a hablar español contigo. Ok, vamos a empezar. All right. So, this is, oops, did I change the camera yet? Okay. So this is AP Physics C, March 1st, period 5. So the topic of today's lesson is Gauss's law. In spherically symmetric systems. Okay, that's the topic for today's lesson. And so just to remind you about spherically symmetric systems, if you have a spherically symmetric system, then that means that the electric field points radially outward or inward, So that means you have the center of your charge distribution. The electric field points directly away from that. Okay. And we are going to choose a spherical Gaussian surface. Okay. So if we do Gauss's law for a spherically, so you have some spherically symmetric distribution of charge, and your Gaussian surface is a sphere. Okay. The electric field points outward. And the area vector also points outward. So what that means is when you have Gauss's law, which says that the flux of the electric field is equal to charge enclosed over epsilon naught, this becomes E times A. All right. Because a spherical Gaussian surface is just one curved face, so there's only one EA. And furthermore, the area vector is parallel to the electric field, and so your cosine theta term ends up just being equal to 1. Okay? So you have EA equals charge enclosed over epsilon naught. Now, it is a spherical surface, so the area of a sphere is 4 pi r squared. All right. So, we can divide both sides by 4 pi r squared, and we get that the electric field is charge enclosed over 4 pi epsilon naught r squared. Boom. So this is what Gauss's law gives us if we have a spherically symmetric system. Okay? So there you have it. One of the things I want to point out is we could think about, I'm going to write it up here actually because this is kind of an aside. Charge enclosed is basically the same thing as mass below. So remember when we were learning about gravitational fields, and we had G equals big G times mass below over r squared, and the gravitational field pointed inward, so I put a negative sign there. Okay, so actually you already know about Gauss's law for a spherical surface, for spherical systems, because we already talked about it when we talked about gravitational fields. Okay, in fact, there is a Gauss's law for gravity, and it is this. It says that the flux of the gravitational field is equal to minus 4 pi g times the mass enclosed by the Gaussian surface. Kind of interesting, huh? It's the same law, exact same law. Okay, so let's basically this lesson is all about practicing this. Okay, so what if we have, I'm going to do an example. What if we have a system that looks like this? So we've got a point charge. It has a value plus q in the center. And then we have a shell of charge. So this is a shell of charge with radius A and charge minus 2q. Okay. And then around that is a conducting shell. So this is a conducting shell, so I'm going to shade it in. Okay. So this right here is a conducting shell. Of net charge, so it's not a neutral conductor, it's a conductor with, so a conducting shell of net charge, let me make this a little bit more clear. And we're going to say plus 5q. All right. So it has a net charge on it, and it extends from R equals B to R equals C. All right, and what we want to do is we want to find the electric field as a function of distance away from the center. Okay, and then graph it. So I'm going to break the problem up into, I guess, 1, 2, 3, 4 parts. Okay, because the charge enclosed by the Gaussian surface depends on how big the Gaussian surface is, and the charge enclosed is going to change as we make the Gaussian surface bigger and bigger and bigger. Okay, so the first region is R less than A. So that is the region in between the central charge and this first spherical shell of charge with an amount negative 2q. Okay, so that is the first region. The second region is the region in between this shell of charge and the conducting shell. Okay, so that is R between A and B. The third region is inside the conductor. Now the conducting shell extends, it's thick. It's not a thin conducting shell, it's a thick conducting shell. It extends from R equals B to R equals C. So we have that. And then, lastly, we could have our Gaussian surface so big that it is completely outside everything, so it's enclosing all of the charge. So that would be R greater than C. Okay? So what we have to do is we have to figure out the charge enclosed by a Gaussian surface of each of those sizes. Okay? All right. So who can tell me if you have a Gaussian surface that is only enclosing this plus Q charge, well, that means that Q enclosed is plus Q. So then plugging that into Gauss's law, we are going to get that the electric field, if R is less than A, is Q over 4 pi epsilon naught R squared. Boom. And it's positive, meaning that the electric field points outward. Who can tell me if our Gaussian surface has a radius that puts it between this region and the second region, what is the charge enclosed going to be? I will wait for someone to type an answer into the chat. Okay? So if your Gaussian surface has a size between A and B, that would mean your Gaussian surface has a radius that's somewhere in between these two regions. How much charge is that Gaussian surface enclosing? Minus Q. Excellent. So if you have a Gaussian surface that's in between here and here, it's enclosing both the central charge and the shell of charge. So the amount that it's enclosing is plus Q, and then this one has a charge minus 2Q. So that would equal minus Q. So Gauss's law is going to give that the electric field is minus Q over 4 pi epsilon naught R squared. So the electric field basically reverses directions and now points inward. All right. Now this one, the third region is really easy. So if your Gaussian surface is between radius B and C, that means that your Gaussian surface is inside the conductor. Okay? So without doing any calculation, who can tell me what is the electric field inside the conductor? Espero tus respuestas. Okay, no one's putting an answer. So there was a lesson where I had you watch it by yourself. I pre-recorded the lesson, and I talked about how inside a conductor, the electric field is always 0. Okay, so the electric field is 0 inside a conductor. So therefore, that means that the charge enclosed would also have to be 0. Okay. So the last case is, what if we have a Gaussian surface that encloses everything? What is going to be the total amount of charge enclosed if it encloses everything? So we have, it's going to enclose the charge in the center, the shell, and the conducting shell, which is not a neutral conductor, meaning that it has a net charge. Type it into the chat if you know. All right, well, I don't have all day to wait. So you have plus Q here. It's enclosing that. You have minus 2Q. Thank you. Yes, you are correct. And then the conducting shell on the outside has a charge of plus 5Q. So if you add all those up, you get plus 4Q. So that means that your electric field is going to be plus 4Q over 4 pi epsilon naught r squared. Okay? So, what is a graph of electric field versus R going to look like? Well, we've got a couple of key values. So the values where it switches are when R equals A, R equals B, and R equals C. So I'll put those three in here. A, B, C. So this is obviously not to scale compared to the way I drew it here. But so when R is less than A, we have plus Q over 4 pi epsilon naught R squared. So this is going to look like a graph of y equals 1 over x squared, which looks like this. It goes like that. And then when R is between A and B, it's now equal to minus Q over 4 pi r squared, 4 pi epsilon naught r squared. So that means that it's going to abruptly change sign to this value, and it's going to, so now it's going to look like a graph of y equals negative 1 over x squared, okay? And it's going to continue to decrease. And then when R is between B and C, the electric field is 0. So it's going to be 0 for a while. And then when R is greater than C, it's like 4Q over 4 pi epsilon naught r squared. So that would be like a graph of y equals 4 over x squared. So the graph is going to be positive again. It's going to jump up and continue to decrease, like so. So that is a graph of how the electric field would depend on distance. So I hope that made sense. The size of the Gaussian surface determines how much charge it encloses. Okay, and yeah, so you basically just plug it into this formula and count up the amount of charge inside the Gaussian surface. Now, one common thing is we often need to know the charges on the conductor. Okay, so remember, again, in that lesson where I was gone and I pre-recorded the lesson, I talked about how the charge on a conductor, okay, has to live on its surface. So it lives on its surface. Okay. There's no charge on the interior of a conductor. It's all on the surface. So this is a conducting shell. So it has an inner surface and an outer surface. So there's some charge on the inside surface and there's some charge on the outside surface. Okay. So what we can do is we can figure out what is the charge on the inner surface of the conductor and what is the charge on the outer surface. Okay. And so what we do, if we want to know what is the charge on the inner surface, well, we know that the electric field is 0 inside the conductor. So that means that if we have a Gaussian surface that is inside the conductor, it encloses 0 charge, right? Because if we have 0 on the left-hand side, R isn't 0, so we've got to have 0 charge enclosed. Okay? So if we had a Gaussian surface that was right here, in between the shell and the conductor, it enclosed minus Q of charge. So the inner surface has to have an additional amount of charge that makes the total charge enclosed 0. So that means that the inner surface has plus Q of charge. Okay. So the reason for that is that this amount of charge makes Q enclosed equals 0, so that the electric field is equal to 0 in the conductor. Okay, so this interior surface, the interior surface of this conductor is going to have a charge plus Q. All right. Then, to get the amount of charge on the outer surface, what you have to do is you have to look at the net charge of the conductor. So that the net charge of the conductor is plus 5Q. So if the inner surface has plus Q, then the outer surface would have to have the rest of the charge, so plus 4Q. Because if we add up the inner surface and the outer surface, we get plus 5Q, which is what I said right here. Okay, so the outer surface has the rest of the charge. Okay. I would say most of the time you don't have a charged conductor, you have an uncharged neutral conductor, in which case the inner and the outer surfaces have opposite charges. Okay. So we'll do another example. So my next question is, what if we have a continuous spherically symmetric distribution of charge. Okay, so this was not a continuous distribution of charge because we have just charge in the center, and then we have an abrupt transition to more charge, and then an abrupt transition to more charge. So this graph has all these jumps in it as a result of these abrupt changes in the amount of charge. But what if we have a continuous spherically symmetric distribution of charge? Well, in that case, okay, excuse me. In this case, we have you will be given a density, charge density as a function of R. So charge density, this is the amount of charge per volume. Charge per volume. So the units of rho, so that's the Greek letter rho, stands for charge per volume, would be coulombs per cubic meter. All right. So how can we get the charge enclosed? Well, what we do is we take both sides of this equation and we multiply by dV. So we have dq equals rho dV, like that. So then what does that mean, d volume? All right. Well, our Gaussian surface is a sphere. Spherical Gaussian surface. And a spherical Gaussian surface is going to have a volume of 4/3 pi r squared, r cubed, excuse me. All right. So taking the derivative of that equation gives us that dV dr equals, so taking the derivative of that gives us 4 pi r squared, because you bring the 3 down. Then what you do is you multiply both sides by dr, excuse me, and you get that dV is equal to 4 pi r squared dr. So this is what dV is for a spherically symmetric system. So you then plug that in, okay? And so you get dq equals rho dq equals rho times 4 pi r squared dr. All right, so now how do we get the total amount of charge enclosed? We integrate both sides. So the charge enclosed is equal to the integral of rho times 4 pi r squared dr from 0 to, I will call it r sub g, where r sub g is the radius of the Gaussian sphere. Okay? So this, if you have a continuous distribution of charge, meaning you're given a rho, you have to do an integral to figure out the charge enclosed. So it's exactly the same. If you have a discrete distribution of charge, then based on the size of your Gaussian surface, you just count up the individual charges inside it to get the value of charge enclosed. But if you have a continuous distribution of charge, then you need to do an integral. Okay, so let's see how that works. Okay, so let's do an example. Have you guys ever heard of the how if you have a hydrogen atom, or if you have an atom, that the electrons are actually in a cloud? Okay, so it turns out that the electron cloud is basically like a cloud of charge density. So inside an atom, the electric field changes with distance from the center of the atom according to Gauss's law, where this is the charge density caused by the electron cloud, because the electron isn't just in one place, it's spread out, it's in a cloud now. So in a hydrogen atom, the charge density of the charge density as a function of r is equal to Q times the quantity 1 wait a second. I'm just going to say, we're just going to talk about the electrons and not worry about because there's also the proton. So if you were to do a Gaussian surface in a hydrogen atom, that Gaussian surface would enclose the proton in the nucleus, and then it would also enclose part of the electron cloud. So, so what we're going to do is we're going to figure out just what is the electric field due to the electrons. So the charge density of the electron cloud as a function of r is equal to some constant times e to the minus r over a, where c and a are constants, okay, that describe the properties of that electron cloud, okay? So what we want to do is we want to calculate the electric field as a function of r, and this is the electric field due to the electrons only. Okay. So we have to figure out what is the charge enclosed. Well, the charge enclosed using this is going to be the integral. I'm going to call it big R. So big R is the radius at which we're calculating the electric field, times the integral of that, the charge density, which is c e to the minus r over a, times 4 pi r squared dr. C and 4 pi are constants, so I can factor them out. And then we have to do this integral. I'm guessing that most of you do not know how to do this integral. This is an integral that can only be done using a method called integration by parts. And I don't know if you guys learned integration by parts. I think you do in Calc BC, but I don't think you learn it in Calc AB. So what we're going to do is we are going to go ahead and plug it into Wolframalpha. So I'm going to change the scene to Wolframalpha. So what I'm going to do is I'm going to say integrate e to the minus r over a being a constant, times r squared from 0 to big R. And it says that the answer is, so the answer is kind of nasty. So I'm writing this down on the piece of paper. 4 pi c times times the quantity 2a cubed minus a times e to the minus r over a times 2a squared plus 2a r plus r squared. Okay. So I wrote down the answer. So that's the charge enclosed as a function of the radius of the Gaussian surface. And then I plug that in to Gauss's law, which says that the charge enclosed over 4 pi epsilon naught r squared is the electric field. So the 4 pi's are going to cancel out. So I will get C over epsilon naught r squared times the quantity, 2a cubed minus a e to the minus r over a. There's 2a squared plus 2a r plus r squared. All right. So that's not a very nice answer, okay? So I just came up with this problem on the fly, so I probably will change it for next class period because that's maybe a little bit too complicated. But let's just see, how does the electric field depend on distance from the center of the hydrogen atom? And so to get an idea of what this looks like, I'm going to go ahead and set C equal to 1, epsilon naught equal to 1, and A equal to 1. Okay? So just because I want to know, what does this graph look like? Okay? So I have my electric field as a function of R is going to be, so setting those all equal to 1 over R squared times 2 minus e to the minus r times 2 plus 2r plus r squared. So that's making those substitutions. So now what I can go ahead and do is I can go to Desmos, and I can just type in the same form as that function. So I had 1 over r squared, so I'll put 1 over x squared, times the quantity, times the quantity 2 minus e to the negative r, times the quantity 2 plus 2r plus r squared. Oops. All right. So if we, and I'll multiply it by like maybe 10 to make it bigger. So we can see that the electric field kind of reaches a peak value right here, and then it slowly drops to 0. So kind of interesting. So this is the size of the electric field due to the electron cloud surrounding a hydrogen atom. So when you guys do the homework, the charge density as a function of distance will just be a simple monomial, so like r to the n. And so that integral will be super easy to do and then plug into Gauss's law. Okay, so I hope that made sense. I think you'll find that the homework is a lot simpler than maybe I made it sound in the lesson. That's my hope, at least. I will see you in the Zoom room.